Thank you so much for having me. It's a real pleasure to speak to this group. I know it to be very engaged and bright group, and so I hope we have some fun discussions at the end. I'll be talking about Argentina, but and I think a few of you have worked there, and I've seen a few of my students show up in the chat and the participants here. But if you don't work in Argentina, I hope that there are still connections that we can make in terms of tectonics that are, similar in Canada or in other parts of the world with what we're doing in Argentina. Let's see, a couple caveats. I have a 6-year-old at home today. She doesn't have COVID, but she has a cold. And so she's on her iPad playing Minecraft right now. So hopefully she stays put where she is, but she may pop in, and that's just the way it is. Sort of reminds me, if anyone wants to have a conversation at the end of this talk about things beyond science, I'm happy to do that as well. Talk about how we're all balancing, life in this COVID world, or talking about being a parent and a scientist as well, or even being chair of a department, which is a challenge. Anyway, so with that said, let me start talking about Argentina. So I'll be talking about how plateaus grow with the Puna Plateau in Northwest Argentina as the sort of case study. And as I was putting this together, it turns out that in 2009, I was giving a talk that had almost exactly the same title. So I've been working in Argentina since around 2004, and about 5 years in, we had enough of a story together to start giving this sort of synthesis kind of talk. But over the last additional decade, I think we've really nailed down the story. And it's a really nice moment, I think, to do another synthesis. So I'm really pleased to be able to, this was a good opportunity to sort of bring together the work that we've been doing over the last 10 or 15 years. And a lot of this work, in fact, most of it has been done by some really excellent students that I've had the pleasure to work with, a number of whom are in the audience today. And so at the end, if there are questions, I may actually throw them to the students because many of them will be able to answer them better than I could. So to introduce them specifically, in order of the time in which they graduated, first we have Ranji Joe. So he finished, I believe, in 2015. He was doing thermochronology and mapping in the southern Puna Plateau. He's now a professor at University of Queensland. So he's up very early, I think, if he's here to make this talk. And then Alex Tai, who is here. Alex was a postdoc during the COVID year. So he started in January of 2020 and finished in December of 2020. So I didn't see a lot of him in person, but he did get into the field, did some really excellent work on the Antofalla fault system, which you'll see shortly. And he's currently a professor at Dixie State University. And then there's Erin Segren, who's also here. And Erin finished in the spring of 2021, so a year ago. And she's now doing a postdoc at Simon Fraser. And then last is Mitchell Macmillan. So Mitchell's my current PhD student. We're just working on scheduling his defense right now, which should be in April of 2022. Interestingly enough, of all of these photos, only one, this one down here, is actually taken in Argentina, and this is from Argentina as well. So you can see that my students and postdocs have all done excellent work all around the world. Okay, so with that said, let's jump into looking at the geology of the Puna Plateau. I'll be using this map quite a bit for reference. I'm using figures from all over the place, and so it might be a little bit hard to track from figure to figure. So hopefully this map over here on the left will serve as a reference for where we are. So we are in South America, in the Andes, and the Altiplano Plateau is where it widens out up here, and then the Puna Plateau here in the south in Northwest Argentina and Chile. So here's the geology. So we've got the Western Cordillera, which is sprinkled with volcanoes, and the Altiplano and Puno, which again sort of widen out. So it's high elevation, but relatively low relief parts of the orogenic system. And then in the north, this is up in Bolivia, we have this classic fold and thrust belt in the Eastern Cordillera and the Subandean zone. And as you come south, it gets more complicated. So if you go quite a bit south, you get into the Sierras Pampeanas, which is this classic thick skin deformation where you have uplift of basement ranges along usually inverted normal faults. And you have deformation far inboard of the plate boundary. Probably, helped in part along by flat slab subduction. And then between those two zones, we get things that are pretty complicated, including here in the Santa Barbara ranges. And so I'll be talking about that quite a bit more as we go through. And this is what it looks like. So this is a strange view, but it's looking from the northwest towards the southeast across the plateau. So we're looking towards the southeast here. And you might want to put the border of the plateau right here, but in fact, the border is actually here. So you can see this high, dry, very low vegetation plateau sprinkled with volcanoes. And there's also these large salars like here. And then as you go off the plateau, you get into these marginal basins. So these are restricted basins. They still have outlets. They manage to cut through these uplifting ranges, but they're constricted and semi-arid. And then you get out into the foreland here. It'll happen sort of the middle of the talk, but I'm going to be talking about two places quite a bit. The first one is the Salar de Arazaro. So it's this big roundish kind of thing right in here. Well, it's funny shaped, but it's got a more even aspect ratio than a lot of basins on the Puna Plateau. So that's the Arazaro Basin. And then there's this long skinny one right here, which is the Antofalla Basin. And you can see also throughout the Puna, there's a strong north-south structural grain. Both a lot of the older fault systems and some of the recent extension follow this north-south structural grain. Okay. So I have three major, and this is what it looks like on the ground. So you might think no vegetation means 100% exposure, so it should be really fantastic mapping. But as it turns out, it's actually, there's this sort of colluvial sludge that covers almost everything. So there's not a lot of excavation of material, so it sort of weathers in place and then slowly moves down the hillsides, covering all the stuff that you want to look at up. And you get kind of weird weathering lines. So it can be surprisingly hard to map despite the low vegetation. I think I've probably only put my hands on faults about a dozen times while working in the Puna Plateau, since the mid 2000s. That's not true when you get off the plateau in the marginal basins, but on the plateau, it looks like this. You can see also not a lot of people or a lot of roads or infrastructure. So there is a main central artery road that, that goes through this region, and there's dirt tracks. And it's not too hard as long as you're careful about what kind of ground you're driving on to, just to drive across these big alluvial surfaces. But nonetheless, it is difficult to access, and it's a difficult place to work. It's high, dry, very windy, and pretty cold most of the year. So I'm going to be talking about three main topics. And like I said, this is a synthesis trying to tell you where we are at this point in our research on the Puna Plateau. And so the first part, we'll be talking about models for crustal deformation. So basically, how do you get thick crust in the first place? And then in the middle of the talk, I'll be covering lithospheric foundering. So once you get thick crust, what happens? And in particular, what does it look like if you lose part of the mantle lithosphere and part of the lower crust into the asthenospheres through lithospheric foundering? And then at the end, we'll talk about climate tectonic interactions. So you have thick crust, and maybe it's high and so on because of lithospheric foundering. But if you've got aggressive river systems, you would be able to tap into and then rip out material from the plateau, and so it may not be preserved. So preserving the plateau probably has a lot to do with what's going on along the margins. So that's the last part of the talk today. So starting with this models for crustal deformation. These two schematic cross sections are from a nice summary paper from the Strecker group, where he introduced this idea in the Andes for the broken Forland basin system. So in the top model, the idea is that you basically have a normal propagating wedge and the attendant sedimentary features such as a 4-deep and a 4-bulge that you should be able to recognize, and they should propagate west to east across the region with time. Now up in Bolivia, no problem, you've got this nice passive margin sequence. When you get down into the Santa Barbara ranges in the northern Puna here, your rocks aren't quite so favorable for that. And so you end up, because you have the Salta Rift, which is a Cretaceous rifting event that has peppered your region with these pre-existing steep faults. And it also gives you only a relatively thin sedimentary cover. And so this orogenic wedge would likely be a thick skin type, so a lot of basement involvement. So you can contrast that with this model for a broken foreland, in which you have uplift of basement ranges along pre-existing weaknesses like inverted normal faults. But uplift is happening in a disorganized way. So you get a lot of out of sequence deformation. So a range that is far inboard of the plate boundary can uplift before one that's closer to it. And one of the defining features is basin compartmentalization. So you don't have a continuous foreland, but rather you have a broken foreland with a lot of local deposition adjacent to these uplifting ranges. So let me walk through the evidence for both of these in the northern Puna, where we've done a little work, but not much. And then I'll talk about the southern Puna, where we've done quite a bit more. Okay, so this is a summary, work. So a lot of people have been involved in this, but Peter de Sells is the first author on this particular paper. This is evidence for propagation of an orogenic wedge through the northern Puna Plateau. So you'd be looking for things like the timing of exhumation of various ranges, but really importantly, they're looking at the sedimentary signatures. So they're trying to identify things like 4 deep and a 4 bulge in the sedimentary record, date it, and try to track the location of these features across the range through time. And you can see that they have. So they have pretty clear west to east propagation. And it's interesting, it's not steady propagation. There's periods where there's relative stagnation. And then there'll be a period where there's a rapid advance. So around 40 MA, for example, there's a rapid advance from the Western Cordillera all the way into the Eastern Cordillera. And then relative stagnation again. And then there's a relatively rapid advance from the Eastern Cordillera into the current deformation front in the last couple of million years. I just want you to briefly rest your eyes on this Roto Basin thing up here. We're going to come back to that later, but just remember that it's there. Okay, so this looks like strong evidence for a propagating orogenic wedge, and there's that interesting stagnation and then quick advance. And these authors suggest it has to do with what they're calling orogenic cyclicity. So the idea is for a period of time, you're building up mass in the origin, and you're building up a thick lithospheric root, and then eventually through magmatic underplating as well as just crustal shortening. And then eventually, and while you're doing that, the mountain range is kind of getting thicker, but it's being pulled down by this dense root. And so it's kind of stagnating in place. And then once that root drops off, your pile sort of bounces back up isostatically. It results in some gravitational collapse or extension in the region, and that causes a rapid propagation of deformation. So you jump your deformation front out, and then you recharge, and you have stagnation during this recharge period, and then you can repeat the cycle again. So they would suggest that they see 2 cycles of this of discharging, basically, in this rapid advancing, one relatively recent in the northern Puna Plateau. So that sounds convincing, but let me talk then about the broken Foreland model. So this is a proposal more or less for the same area, and it's based on thermochronology and the sedimentology of adjacent basins in the Santa Barbara ranges. And so starting down here, we have a relatively unbroken Foreland basin, and then we have uplift of this Matan range around 10 MA, and then it jumps back. So it's out of sequence deformation, and then it jumps again in the Quaternary out to the Santa Barbara ranges, which is way out here. And so the emphasis here is on the uplift of these discrete basement blocks and compartmentalization of the Foreland and out of sequence deformation. So this is all work that's been done in the northern part of the Puna Plateau. And as I mentioned, we wanted to look at the southern Puna. And so this is some work that Ranji Joe did. So he's on the call, I think, today. And Ranji, like I said, did detrital thermochronology and mapping, bedrock thermochronology in the southern Puna. And so this is a figure from one of his papers. And you can see he's identified this Paleocene deformation front and late Eocene deformation front based on the existing literature for the Altiplano and the northern Puna. But until his work, there really wasn't good data for the southern Puna Plateau. And so he did some original work and compiled other studies to figure out what's going on in the south. And right away, you can see that there is some curvature here. The timing of deformation is stepped westward relative to the rest of the front in the southern Puna Plateau. And so that led him to propose this nice model here, where we have a more advanced deformation front in the northern Puna in the late Eocene to early Oligocene, and potentially a transfer structure between the two, with deformation kind of recessed a bit in the southern Puna. And so this gray boxes up here are showing the earliest onset of deformation as you go across the range from west to east. And you can see that there's this early deformation in the Eocene in this area here called the Sierra Chango Real. And so, you can see in Ranji's model, he's suggesting that there is early uplift here as well. So that looks like more of a wedge that's propagating into an area that does have some basement uplifts that looks more reminiscent of the broken Foreland. So he's seeing both operating. In the north, less of that is going on because of the existence of Cretaceous rifting structures in a thin sedimentary cover. So he sees a stronger broken foreland in the south than in the north. However, some of these data are inferred or not our own. So this column B, you can imagine there could be a bit of refinement there of the deformation record from the sediments in the Antofalla Basin. And for example, this data here, this is the Quebrada Honda range, and this was just inferred from detrital thermochronology. So we spent some time investigating this region further to try to fill out this story more clearly. So I'm going to show you that next. So this is a map that my current PhD student, Mitchell Macmillan, produced. I hope you find it as beautiful as I do. I think it's really extraordinary. You know, a lot of, there is a base map that is quite good from 2006, but he really answered a lot of questions that hadn't been before, particularly in this Salina de Farile, here in this Campo Negro region. And then you can see along this transect right here, he really answered some of these questions about previously undifferentiated sediments and so on. And I'd also, like an aside, I guess, he was making this map in March of 2020, and I have this really vivid memory of calling him on Friday, it would have been the 13th of March, on his satellite phone and saying, Mitchell, you probably haven't heard much about it being where you are, but there's this thing called a global pandemic and you need to get on a plane and come home. So he truncated his field season, but despite that, it turned out a beautiful map. And so here is the cross section. And right away, you should be able to see that there's a bunch of west vergent structures. So that is, these are back thrusts in the, in the overall orogenic wedge, except over here when you get to what's called the Quebrada Honda. And so his work, he did this, this beautiful map. You can also see there's a number of unconformities in here that he identified. And he also did, detrital zircon dating of some of these strata. And he has bedrock samples from Macalasta, from this Campo Negro right here, so on the western side of the Antofalla Basin, from this little anticline that's just poking up right here in Fraile, and then over here in Quebrada Honda. And these are all, except for Calolasta, which had been looked at before, these are all new. So on the basis of this work, he put together, this diagram here. Here's the cross section at the bottom. And so adding to the story of deformation and sedimentation in the Puna Plateau, we have now quite early deformation. This is the oldest recognized in the Calolasta, around 55, 60 million years ago. And then there's another little bump in deformation in the Eocene. And then we have this fairly nice looking east, I always get it wrong because it's counter to what I would expect, east to west propagation of deformation, including these identified growth strata in the late Oligocene to middle Miocene. And then we've got the Quebrada Honda over here, previously not officially dated, but now it is, so around 30 MA. So he argues for an earlier phase of more broken foreland style deformation or shortening, similar to what Ranji saw across the whole region. And then this late Oligocene, middle Miocene wedge, but in the back thrust sense. And just like I said before for the northern Puna and that Descelles figure that looked like this one, just quickly rest your eyes on this little guy up here, which is a period of extension followed by shortening. And we'll come back to that in the next part of the talk. Okay, so now I'd like to layer this onto this diagram from Ranji. So we've now added earlier deformation in the Calolasta range, actually 2 phases of it. We've refined the timing of deformation in the Quebrada Honda. It's a little bit younger than we thought before. And so this would be the sort of broken foreland phase down in here. And then we have this west to east propagation of deformation, which just looks like back thrusting within this orogenic wedge. So we refined that picture, I think, considerably. Okay, so to answer this question about which is it an orogenic wedge or is it a broken foreland? I think not surprising when you have sort of end member or competing models, the answer is both. So we think that perhaps the region looked more like a broken foreland basin system early on, and in the southern Puna at least evolved more towards this orogenic wedge later on. But we don't see these 2 models as being exclusive of each other, and so we think that both were operating. And that you were building up a wedge with time, but propagating into a very complicated region. Okay, That was part one, and now I'm going to make the transition into part two. And so if you recall, I said rest your eyes, but don't pay a lot of attention to the stuff going on in this part of the diagram. So now is the time to do that. Mitchell's work identified that there's this period of transient extension in around 11 MA in the Antofalla Basin, followed by renewed compression. So a little flash of extension that then is replaced later by horizontal contraction. And then we actually see the opposite here in the Arizaro Basin. So it's very much out of sequence deformation with contraction followed by extension in the last 20 million years. So what is the cause of this? It's happening way in the interior of the plateau. Well, we think that the answer, or quite confident that the answer has to do with lithospheric foundering. So that's the next thing I'm going to walk you through. So lithospheric foundering has been long proposed. It's coming up on the 30-year anniversary of the very important K&K paper, where they initially suggested removal of part of the mantle lithosphere underneath, and part of the crust actually underneath the Puna Plateau. And that was based mostly at that time on the signature of mafic volcanics at the surface of the plateau. So we've thought about this for a long time. And I think there is fairly smoking gun evidence. This is a P-wave tomography, and you can see the slab. And as you go deeper, you can see it, moving to the east because the slab is dipping to the east. And there's this slow region right here, A, and then the slow region B here, and it's starting to disappear right here. And if you look at them in cross section, this is what they look like. So here's that blob A right there, and here's the blob B right here. And so they look very much like fast regions, which potentially are cooler founded mantle lithosphere, which is sinking into the asthenosphere. And this blob B is sort of resting right on the slab itself. So we see, I think, very strong evidence that there has been a removal of mantle lithosphere. And so the question for us isn't did it happen, but I think the question is how and when, and what did it look like at the surface? What can we use to identify the extent over which this region was influenced by the lithospheric foundering at the surface? So what do we expect to see at the surface? So I'm going to try to answer some of those questions in the next segment of the talk. But in order to do that, I want to step back for a minute and talk about lithospheric foundering in general. So this is a really nice compilation, like extensive and very impressive, I would say, compilation that my student Mitchell Macmillan has put together. And what he did was two parts. The first thing is he identified all of the purported lithospheric foundering events, Rayleigh-Taylor instability that are out there in the literature. There's different forms in which you can remove mantle lithosphere through delamination or through these dripping, which is the formation of a Rayleigh-Taylor instability, or something in the middle. But he was focused on these Rayleigh-Taylor instabilities. So there are 25 out there that we were able to find in the literature. Some are very well studied, like in the Sierra Nevada, or actually in the Puna Plateau, and some are less studied and maybe only have a paper or two in support of them. But nonetheless, he looked at all of them with the question in mind of, are there patterns? Are all drips similar in size and have similar expression, or are there multiple types of expression? And so is there a pattern to our observations of real drips in the real world? And then the same thing looking at the modeling literature. So lots of people have tried to model these things using different programs, different assumptions. Some are in, fewer in 3D, not many, many are in 2D, and some of them are analytical. So we looked at that literature as well, again, to see if there are any patterns. Is there a way that we can, carve through some of the confusion and see whether or not there's underlying patterns and similarities among drips? And in fact, he found that there is a similarity. And so he identified what he is calling strong crust and weak crust drips. To be clear, these are not end members. These are just sort of points along a spectrum of behaviors that seem to be quite common. So, clusters of drips, there's types of drips seem to cluster around these two categories. But again, there's a spectrum of behavior. A lot of real world drips are not very well constrained. But in general, I think it's a really useful framework for looking at drips. So let's walk through it briefly. So on the left, you see a strong crust drip. I think this is more what people think of when they think of lithospheric foundering. And the idea is that as the drip is gathering and forming, it's pulling material towards it. And if the crustal viscosity is an order of magnitude or greater than the viscosity of the mantle lithosphere, the crust behaves in a relatively strong way. So it's sort of fixed here, and it behaves in a semi-flexural way, so that when you're pulling down on the plate, you're pulling down on the crust and you're producing a basin here. And that basin would experience compression during its formation. So you have a compressional subsiding basin above the drip. And then when the drip detaches, that anchor is removed. And so you have isostatic uplift of the region, and that can invert your structures and produce a high where previously you had a compressional low. In a weak crust drip, this is a scenario where the crust is less than an order of magnitude stronger, its viscosity is less than an order of magnitude greater than that of the mantle lithosphere. The crust deforms in a different way. As material in the mantle lithosphere is sucked towards this drip, you're actually advecting or pulling along the upper crust as well, and it results in crustal thickening and this little bit of an upwelling right here. And so right above the center of this thick crust, you have a bit of extension. And then when the drip detaches, you have a broader region of extension because you've got this thick pile of hot crust, which is now collapsing under its own weight, essentially. Both of these models would predict mafic volcanism at the surface as a result of this asthenosphere moving up closer to the surface and melting. They would both predict ignimbritic volcanism or felsic volcanism as well, because you have crustal melting post-drip detachment. And you also could have potentially melting of the drip, particularly if the drip is relatively small. You can actually melt this drip material and that would make its way back up to the surface. So these are all the sorts of things that we want to be looking for. Now, let's generalize a little bit further, or maybe I should say synthesize a bit further what you would see if you're looking for a drip at the surface. So Mitchell and I developed these diagrams. Time is on the x-axis here. So, and distance is sort of schematically shown, at least for the teardrop shape of the drip, but these little observables are arranged randomly. So, this is the sort of phase showing the drip gathering, and then the drip detaches, is marked by this bar, and then the sort of effects of it are tapering off in this direction. So let's look at the commonalities first. We would expect that you might have a little bit of mafic volcanism before the drip detaches, but you should have a lot of it afterwards, and also you could have felsic volcanism as well, so ignimbrites erupting. Xenoliths will change composition. You'll have a root absent or a root present before and after. That's not something we see much of in the Puna Plateau, but it's important for other drips around the world. So the big difference between the two, the idealized weak crust drip versus strong, has to do with the timing of shortening and subsidence and extension and uplift. So you would expect with the weak crust drip that you would have surface uplift before the drip detaches as you're thickening the crust, and you have a little bit of localized extension here, and then it would spread out after drip detachment. Whereas with the strong crust drip, you expect strong subsidence with shortening, concomitant shortening before drip detachment, and then it flips afterwards. So keeping this model in mind, let's take a look again at the Puna Plateau. All right, so I'm going to be using this diagram quite a bit in the next few slides, just sort of layering information on top of it. With the information, where the information comes from is going to be here on the right. So what I'm showing in this diagram right now is the contours of the moho. So this is the depth to the moho. And so you can see the crust is relatively thick, 65, well, it's very thick, 65 kilometers in places. It's a bit thinner up here. This is the Roto Basin. And then, so that's this diagram on the right is showing the depth to the moho. The diagram here is showing depth to the lithosphere-asthenosphere boundary. And I know that it is teeny tiny, but I can tell you that that number right there is a 60, and that number right there is also a 60. So the depth to the moho and the depth to the lithosphere-asthenosphere boundary are the same, which means that the lithosphere is essentially absent in this region. So under the entire Puna Plateau and Altiplano, it's thin, and right about here, it's actually completely absent. Okay, so that is suggestive of, you've removed the lithosphere somehow. Okay, here's the geophysics, the tomography that I showed you earlier, drip A and drip B, and this is where they map onto the surface more or less. Here's some helpful ignimbrites. So we have this aguas calientes that erupted around 17 MA. And remember, we expect to have this kind of volcanism immediately post-drip. So that might already be telling us about the timing of this drip. And then we have the Cerro Golan down here erupting around 7 MA. And we also expect mafic volcanism. So these are not all of the flows, but these are all of the dated flows that we have across the plateau. And you can see they're centered here around this skinny feature, which is the Antofalla Basin. And the oldest ones are 8.7 MA. And the youngest ones, at the edges are quite young. And in fact, this is just for fun, but there's this one flow right here, which we actually got a negative age on. So it's basically erupted yesterday. It's very young. So it's essentially active volcanism on the plateau surface. And it's these small volume cinder cones and small flows that are quite beautiful. So not only are they beautiful, but they are also geochemically interesting. And I won't be able to explain all of this, but when you have composition that is closer to this pyroxenite end member, it suggests that what you're seeing isn't a cenosphere melting. That would give you more of this peridotite composition, but it's actually wet melting of the sinking lithosphere. So you're actually seeing the drip itself as it descends into the asthenosphere and heats up. It melts, and some of that makes it back up to the surface. So we're actually seeing that product here. Okay, we also said that you might see a lot of extension, particularly in the case of a weak crust drip. And so all of these little blue lines show our extensional faults, and this fat blue one we're going to talk about in more detail. And notice that this is also focused around the Antofalla region, and you don't get much of it around Arizaro up here in the north. And sedimentary basins was another thing we said to look out for. And so here's a big sedimentary basin in the Arizaro region. And in Antofalla, we have some sedimentation, but not as much. Okay, so having laid all of that out, now we can talk about the two potential dripping events that we think we have observed in the Puna Plateau. And they correspond to these two tomographically imaged blobs. So the first is in Arizaro, and because of the presence of this basin and because of the absence of significant normal faulting, we think that we're actually looking at a strong crust drip here. So let me zoom in a couple times and show you what this area looks like first. So this is an image from the Arizaro Basin, and it is this monotonous several kilometers of just this red mudstone. With occasionally you get excited because there's gypsum or something in it, but it's this really monotonous pile of rocks. And Peter Sells and others, Brian Horton, Barbara Krappa, have done work through this basin, and they did the painful work of doing all the PMAG to try to get dating on these sediments. And so they've mapped through here, and on this basis, they are able to generate this subsidence curve for the basin. So you can see that it was, and then here's the backstripped version. So this is the tectonic subsidence. So you can see it gets sort of a slow start around 20 MA. It really takes off dramatically around 17 to 16 MA with rapid subsidence, and then it tapers off after that. And you can see just looking at the map that there's no other culprit for subsidence. There's no adjacent mountain range. So this isn't in the flexural basin in front of a local uplift or anything like that. And so they attribute this formation of this basin to formation of a lithospheric drip that pulls down and creates a hole at the surface that's compressing. You can see these thrust faults running through here at the same time. And they call it a bobber basin. And Huilin Wang and Claire Curry have done a number of nice modeling studies. This is just one example where they model this behavior, essentially a strong crust drip. And that's what these black lines are. They're showing the predicted subsidence curves for lithospheric founding. And you can see how well they match this subsidence curve for the Arizaro Basin. Another thing you want to see, though, if this is indeed a strong crust drip, is you want to see shortening replaced by extension. So let me briefly show you some of our field work from the western side of the Salar. So all the purple stuff is volcanic clastics. The green are some of these basalt flows that I've mentioned that are all relatively young. They're really beautiful. You can just see it from their map pattern that they're nice. So we have identified shortening structures in the footwall of this big thrust fault running along the west side of the basin. And you can see there's growth strata here, and this purple is an ignimbrite. And we're able to bracket that deformation to being around 17 million years. And then these faults are inverted. You can see that I've shown the double arrow here. These are all normal faults today. And just as a quick example, this flow right here has been offset in a normal sense across this fault, and it's 2.5 MA. So sometime between 17 and 2.5, you have a reversal of deformation along these structures, which is what we would expect. So in summary, strong crust strip up here. And now I'm going to make the case that in the Antofalla region, we have a weak crust strip based largely on the presence of all these extensional faults, and particularly this big guy along the western margin of the Salar. And so for that, I'm going to call on Alex. Alex is here. Alex ties recent work. So this was nearly accepted at Tectonics. I think he resubmitted it today, actually. So he did a really nice study looking at the Antofalla Basin. And people have speculated about there being a large normal fault along the west side of the Salar, creating this weird skinny geometry. But I think Alex has really gathered the evidence in the field and based on mapping relationships to demonstrate it quite conclusively. And a lot of it comes down to just the fact that all these red and orange, brown and orange and yellow sediments across here, we think we're part of a contiguous basin based on paleocurrent and provenance and so on. But now you find stuff on the west side that is older and higher, and you've got stuff on the east side that is younger and structurally lower. And the only way to do that is to either have an east dipping normal fault or a west dipping thrust fault. And I think Alex and Mitchell, based on both the mapping that they've done, make a convincing case that it needs to be an east dipping normal fault along the margin of the basin here. In addition, Alex was actually, as I mentioned, I think, less than a dozen times I've actually put my hand on a fault. So Alex was able to identify this tabular body and identified it as a fault breccia. So he actually sees the fault. And then last, he's done some nice work looking at these normal faults that are, just along the edge of this Antofalla fault. So you can see these little scarps in the slope map right here that he's identified. So convincingly makes the case for extension. And it turns out that that extension is around 11 MA based on the timing of these sediments that are being cut and offset by that fault. And interestingly, we have, after that phase of extension, we have a return to horizontal contraction. And so you can see these, these two features that they've identified where we have shortening of young, relatively young sediments. So shortening after 5.5, you can barely see it down there, or 1.47 MA. So sometime after 11 and before 5 MA, we have a switch from extension back to contraction again. And then he took this a step further and looked at the regional picture. So this is a compilation of evidence. So coming across, figuring out the timing and the style of deformation in this region is not trivial. So this is, several decades of work that, that Alex has, has compiled, and there's still lots of question marks. But basically, he's looked at these, at the timing of deformation in all the regions where that information is available. So each one of these little diagrams is showing time, it's getting younger as you go up, and the colors indicate the sense of deformation. So red indicating horizontal contraction or shortening, and blue indicating extension. So you can see just at a glance all around the Puna Plateau, you go from shortening to extension, shortening to extension, shortening to extension, and so on, except for in one location. And that's right here in the Antofalla Basin, where we have this just transient phase of extension, which again is what you would expect from lithospheric founding. Okay, so to make that case a little bit more clearly, I'm going to turn some modeling work that Mitchell Macmillan is doing. This is in prep right now. And it's beautiful. I have some slides in the gutter at the end of the talk. So if you want to know more about the modeling, we can talk about it then. But he's using a program called Aspect, and there's two innovative things that he's done, I think. One is that he's seeded a bunch of weaknesses in the crust. He has some versions where it's just distributed and some versions where it's distributed, and he's put in sort of pre-existing weaknesses. And these are roughly, correspond to ranges that we see at the surface. So Quebrada Honda and the Kalalasta, for example. And then he's allowing his eclogite to drive the foundering, and he's allowing it to grow sort of spontaneously. So he's, as crustal thickening occurs, you move rocks into the zone where eclogitization happens. And so your eclogite forms naturally and it kind of runs away from itself. So you can see, we've got initially compression across the entire region. And then as the drip starts to grow, right above that drip, as you would predict for a weak crust drip, you have a narrow zone in which you have extension. And then here's the drip detaching. It happens very quickly, around 200,000 years. In model time, it's between 37 and 38 MA. And then once the drip detaches, you have this sort of spreading out, this like flashing across the region of extension. And then it slowly sort of resolves itself. It's a bit asymmetric, so more on the east side. And eventually, because the model overall is in compression, you end up with, compression ruling, things at the end of it. Okay. So how does that compare to what's going on in the Antofalla region of the Puna Plateau? So I'm going to start with this diagram right here, which is confusing but also brilliant. It is showing time on the y-axis increasing in this direction. This is model time over here. And then across in the x direction, it's distance. And each one of these is each sort of horizontal line across here is a time slice at 4 kilometers depth. So for example, if you go across this model up here, you have this little couplet of west dipping structures here, and then there's another pair, and then 1 and 1, right? So if you go across here, here's that couplet, 2 of these structures, that one and that one, right? So each horizontal bar through here is a single time slice at a depth of 4 kilometers through this strain diagram over here. So 15 kilometers is right here and so on. So these blue lines represent faults through time, and you can see them sort of tracking, and it's compressional, so they get closer together over time. And then as you approach the drip detachment, so as the drip is really gathering its head right here, you can see this extension that shows up right in the middle, right above where the drip is going to detach. So that corresponds to this. And then immediately post detachment, you see things sort of flashing across the whole region. So that's here where you find extension across the whole region, and then it resolves itself slowly into just extension to the east, and then goes back to compression. So how does that compare to the real world? This is Mitchell's work looking at what we think are the active structures before 19 MA, which is the same as before 38 MA in model time. So this is while the drip is still in its in nascent phases. Then we see shortening across the region. These are the structures we think were active. And then immediately before drip detachment, so 16 to 8 MA, we have the activation of this Antofalla faults and some of these faults off to the side that Alex has done nice work on. And the rest of the region is in compression. And then post drip detachment, we have a return to shortening in the Antofalla region, and we have extension off to the east. And then eventually we would return to regional compression. So it's a really nice demonstration that this model does work for the region. Okay, so in summary, we think that we have a strong crust drip, 16 to 17 MA in the Arizaro Basin, and around 7 or 8 MA, we have formation and rapid detachment of a weak crust drip in the Antofalla region. So the next question you should be asking yourselves is, why would there be such a difference in behavior from north to south in such a very small part of an origin? You wouldn't expect that much of a difference. I think we have a good answer, but I think this is also something that we would be working on for the next few years to try to figure out. So the explanation, we think, probably has to do with heat. And so this diagram is showing two things. It's going shear wave velocity in the crust, but it's also showing, which I haven't mentioned previously, these northwest, southeast trending lineaments across the region. So this is the Altiplano volcanic, Puna volcanic complex. So it's an area where there's a bunch of mushy stuff down at depth, and you can see it's very, very slow velocities here, and lots of these northeast, northwest, southeast trending structures. In the Arizaro region, though, it's sort of cradled. There's structures to the north and south of it, and you can see that the velocities are faster here. And then you come down to Antofalla and you get structures going right through it, and these red colors again. So it's a little bit slower. So we think that there actually is significant heterogeneity in the crust with stronger and weaker crust, in the places that we would expect it, given the styles of lithospheric foundering. Okay. So with that, I'm going to turn on to the last topic, which is what happens at the plateau margin. So you build stuff up, but what if the rivers rip into it and destroy it? And because the plateau morphology, is really about this region of internal drainage and aridity, and that has a lot to do with surface processes. So, this is something that's known as the bathtub model, but it is probably applicable, but it demonstrates, I think, what I'm talking about. So you have uplift of mountain ranges, and rivers, in order to keep passing through them, have to be able to keep up, and they have to be able to cut through the ranges or between them. Sometimes if the the ranges are segmented, they can go in the sort of relays in between them. But as they uplift, you have a reduction, you have orographic rainfall, and so you get reduction of rainfall in the basin behind, which further reduces the capacity of the rivers to keep up with this uplift. And the idea is eventually you can cut off those rivers completely, and then you end up with this region of internally drained Puna Plateau, which becomes morphologically connected to the plateau. And potentially we think that some of these basins can behave in an oscillatory way. So you might partially close them or close them and then reopen them again. So exactly what's happening at the margin of the Puna Plateau is very interesting. And it's the subject of some work that Aaron Segrin, who is also here, I think, has done. So let me jump onto that. These are, my students all make beautiful figures. So I love this one. This is one of Aaron's strip maps that she's famous for. So it is showing the margin of the Puna Plateau from south to north. That black line right there is the drainage divide. So everything to the west is in the Puna Plateau and it's internally drained, and everything to the east is externally drained. It goes into these marginal basins and then out to the Foreland. So she's looked at the geology. So lithology we think is important. This is the rainfall, the mean annual precipitation. This middle diagram here is showing the NDVI, which is a measure of vegetation. And then over on the right, these are a bit more processed, these two data versions, I guess. So this purple one is showing relief, and then this one on the right is showing the river steepness, with orange and yellow colors as being steeper, normalized to the drainage area. So what do you do with this? Well, Aaron produced these very nice plots. And what you're looking for here is, what the question is there a propensity for the drainage divide to migrate towards one direction or another, or is it stable? And if it's stable, you would expect that the metrics, or the Gilbert metrics we call them, on either side of the drainage divide would be very similar, and therefore there's no propensity for the drainage divide to migrate towards one side or the other. But if they're unbalanced, if relief is higher on one side, for example, or if the channels are steeper on one side, then likely the drainage divide is unstable and it would be migrating over time in order to reach stability. So in each one of these diagrams, each of these slices corresponds to a segment along the Puna Plateau. So this is segment 10 here, which corresponds to segment 10 here. And this is segment 1, which corresponds to segment 1 down here in the south. And then she's plotting the data on one side of the range of the divide versus the other. So we're using orange for the Puna side because it's more arid. It's supposed to be intuitive. And this teal color for the eastern side because it's supposed to be more humid. And what you're looking for, and this is just showing, for example, this top one is headwater channel elevation. So we're looking for a place where there is such an imbalance that there's more than a standard deviation difference between the metrics on one side versus the other. And you can see that headwater channel elevation isn't very helpful. However, if you look at headwater local relief, so that's this purple map right here, there are 3 segments in which there is a significant imbalance. So that's segments 10, 8, and 6. And then if you look at steepness, so that's this guy on the right, there is significant imbalance in segments 10, 8, 6, and then also a little segment 2 down here. So this tells us about the propensity to move in one direction or the other, but then you have to look at it in detail. And so this is Erin's close look at segments 7, 6, and 5, and she's got a similar work for segments 7, 8, 9, and 10, and segments 1, 2, 3, and 4 to the south. And so she's looking for actual evidence of this in the landscape. And you can see by the number of markings on here that there is a lot of evidence. So for example, she's looking for hairpin turns or barbed drainage, which would suggest that the river used to flow in a different direction than it is now. Or looking for things like low spots in the divide or sedimentary deposits, particularly ones that cross the divide, because those suggest that maybe a river used to flow across that region. And so you can see there's lots of things that she's observed. And these red lines right here are all places where she sees strong evidence for recent migration of the drainage divide, in all cases towards the Puna Plateau. And I just want to briefly point out this larger basin up here. This is the Quebrada del Toro, and I'll come back to it in a minute. Okay, and so here's the punchline, the final message of the story. So again, showing the strip map along the margin of the plateau. So everything that is shown in this teal color, these are places where the Foreland has eaten away and taken stolen area from the Puna Plateau. And I would characterize these as nibbles. So there's spots where the plateau has shrunk because of the headward advance of these Foreland rivers, largely through minor drainage captures or for just back wearing of the main drainage divide. And you see it, like we said, in segments 10, 8, 6, and 2, like was predicted by the Gilbermetrics, but you also see it a bit in some of the other segments. And then there's places like this. So this orange basin down here, this is a place where the Puna advanced on the Foreland, and you can see this isn't not a nibble, this is a significant bite. So the Paleo divide would have been back here, and then the Puna, through the constriction of the basin outlet, this region became incorporated into the Puna Plateau. And here's what it looks like. This is actually on the main road through the region, and this is sort of a tourist spot. So if you drive up here ever, it's a nice place to stop and take a photo. There's this giant sand dune, and it's sort of exaggerating the point a little bit because there's a bit of a slope in this direction. So the drainage divide is probably 100, 150 meters or so high. But really, when you're driving up here, it looks like there's just a giant sand dune. So it looks like if you came in here with a couple of bulldozers, you could open up the drainage divide again, and all of this orange stuff would then be able to flow back into the Foreland and into the Atlantic Ocean again. So just sort of emphasizes the precarity of some of these drainage divides. But in this case, this was a big win for the plateau. And then up here in gray, these are basins where others have documented oscillation. This is the Quebrada del Toro Basin. And the red stuff back here is older, but these layered gray conglomerates with this sort of light colored silty lossy stuff in here. This is an example of a basin that we think was partially or fully restricted at some point. It filled up with sediment, and then its outlet was then reopened and the basin incised. And we would predict that over time, that through continued tectonic uplift and aridification of the basin behind it, eventually that outlet will be defeated, and these guys will switch permanently to orange. So we think that the plateau is advancing in these big bites, but it's being nibbled away at by just drainage divide processes. All right, so that is it. Just to summarize, we think that in the northern Puna Plateau, where we have worked less, but still some, there's evidence for propagation generally of a thick-skinned orogenic wedge and detachment of a strong crust drip at 16 or 17 million years. In the southern Puna, we have propagation of the thick-skinned wedge, but into a strongly broken foreland. So we see much more of both of these models in operation. And detachment of a weak crust drip at 7 to 8 MA. And then along the Puna margin, we have minor divide migration, reducing the plateau interior, these little nibbles, but at the same time, we have major increases in the plateau area through basin outlet constrictions, so big bites where the plateau is growing in area over time. So thank you very much for your attention, and I'd be happy to answer any questions that you guys have and engage in a conversation.